All right, so now we're on to linear transformations. These objects are really at the heart of the subject, and all the cool things we do in this field use linear transformations in some way. So what are they? Well, roughly speaking, they're functions, more specifically, they're vector functions that have nice properties. Okay, so, in other words, they interact nicely with algebraic operations. So before we can get on to saying more precisely what that means, let's just remind ourselves what a function really is, formally speaking. Okay, so function, mapping, transformation, all those words refer to the same thing. They're referring to a rule that assigns some object to another object. Okay, so, well, what would that look like? So this part here that I've highlighted is important. This is you can think of this as like a function header or function prototype. It doesn't tell you exactly what the function does, but it tells you how it works. It tells you what to expect from it. So you've got three pieces of this notation, three key pieces of information. So the first thing is the f part. That tells you that the function's name is f. Then you see the capital X. That's telling you that the domain of the function is capital X. So you're expecting capital X to be a set of values. And what that set really represents is it's the set of values that you're allowed to plug into the function. It's what the function is expecting as input. So I'm just going to draw a little example down here. Maybe you've got a set X that has three values in it. So I'm going to say x1, x2, and then I'll put x3 over here. Okay, so that's an example of what your domain might look like. That's a nice small domain, only three values. Okay, and then the other, let's go back to here. So then you see an arrow pointing to another set, so which is capital Y in this case. So capital Y ought to be a set as well, and we refer to that set as the codomain, not to be confused with the range. Okay, the range is something different, but when you see something like this, this tells you that f is the name of the function, x is the domain, and y is the codomain. So what you know now about the function is that you're allowed to plug in values that come from the set x, and you're absolutely guaranteed that the values that the function now spits out as return values are guaranteed to be in the set y. So let's just draw a picture of what the set y might look like. I'll draw a small set in this case as well. So let's say we've got, I'm just going to draw three values again. So I'll say this is y1, say this is y2, and this is y3. So, and then the idea is that your function f is going from x to y. It's a mapping from x into y. Okay, so, well, what's f going to do to the three possible input values in the set x? Well, that isn't clear at this point, right? We'd have to specify that, and that would be where you're actually defining a specific function. So let's come up with some ideas here. Maybe we take x1 and we map it. This is why functions are called mappings. We map the value x1 to the value y1. And then maybe we take the value x2 and we map it to the value y2. And then how about we take the value x3 and we map it to the y1. Tricked you there. You thought I was going to go to y3. But there's no need for things to behave as expected, right? First of all, you see that we've got two distinct input values, x1 and x3, both being mapped to the same output value, y1, and that's okay. Not all the input values are going to get different output values. Although if that is the case, if all of the input values go to distinct output values, then you say the function is injective or one-to-one. And then similarly, not all the values in your codomain are going to even be mapped to at all. They might never actually appear as output values of the function. Although and again, sometimes they will though. If you do have a function that has the property that every single value in the codomain appears as an output value somewhere, well then you say that the function is surjective, or sometimes you'll say onto. Okay, you don't have to worry too much about that terminology, so I'm not going to write that down. And let's write down some notation here. You'd say, if you write f of x1 is equal to y1, you'd say f of x2 is equal to y2, and then you would say that f of x3 is equal to y1, right? Because that's where x3 was sent. It was sent to y1. And one last comment. This is often a source of confusion. If I were to just define a new set that only had y1 and y2, so the specific elements of y that do appear as output values, then this is referred to as the range of the function f. Okay, so the range and the codomain are two different concepts. They might be the same, but they don't need to be the same. So if you see a function header like this, you don't know what the range is, but you do know that the codomain is y. So, but you do know that the range is going to be some subset of y. It may be all of y, but it might not be as well. So in this picture, this is what it might look like if it's not all of y. Okay, so that's just a reminder on how functions work in a formal sense. Let's look at an example in a more concrete case. So here we've got our function header. That's saying f goes from R2 to R2. What that means is it expects a two-dimensional vector as input, and it's promising to give you back a two-dimensional vector as output. Okay, so well, what do we have here? How does the function actually work? Well, that's what's told to us by this rule. Okay, you're not going to use a diagram like this. Diagrams like this are very nice to visualize things, but they're only practical in very small, simple cases. Like in this case, our domain, in this case, our domain only had 3 elements, so it was practical to draw a diagram. But R2, that has infinitely many points. You're not going to be able to define the function using a diagram. But instead, you'll use some sort of a formulaic rule, like you see here. So f takes an input vector that has 2 coordinates, x and y, and then what does it do? Well, it looks like what the function f does is it applies the sine function to the first coordinate, and it applies the cos function to the second coordinate. And using that rule, we can actually calculate some output values from the function f. So here's some examples. So let's look at f of pi over 2, 0. So this means take the vector whose first coordinate is pi over 2 and whose second coordinate is 0, and plug that vector into f and see what you get back as output. So, well, how does the function work? We're going to apply sine to the first coordinate, and we're going to apply cosine to the second coordinate. Okay, and well, you may need to brush up on your trig values, but sine of pi over 2, that is actually equal to 1, and cosine of 0 is also equal to 1. So the output vector here is just the two-dimensional vector whose both coordinates are equal to 1. Okay, so how about part B? We've got f of 0 pi over 2. So now we're taking the vector whose first coordinate is 0 and whose second coordinate is pi over 2, and we're plugging that two-dimensional vector into f. So what's f going to do? Well, it's going to, same thing. It's going to apply sine to the first coordinate, and it's going to apply cosine to the second coordinate. Okay? Well, sine of 0 is just 0, and cosine of pi over 2 is also 0. So you end up getting the 0 vector. Okay, and then what about in part C here? I'll do it down here so we can leave this space for something else for a comment later. So f of pi over 2, well, that's going to be, well, follow the same rule, right? It's going to be the first coordinate is going to be sine of the first coordinate of the input vector, and the second coordinate is going to be the cosine of the second coordinate of the input vector. Okay, so this goes in here, and this goes in here. Okay, just so happened that they were the same value for reasons that will become clear in a moment. There's a reason I chose it like that. So, okay, so, well, sine of pi over 2 is equal to 1, and cosine of pi over 2 is equal to 0. Okay, so that's what we've done here in the example. We've done what was asked, right? We evaluated all 3 of these output values. So, yeah, whenever you see a function and then a vector plugged into the function, what you're saying is this notation represents whatever the output will be when you plug this vector into this function. Okay, and we'll end this page off with an observation. So If we actually gave names to these input vectors, so that this was the first thing we plugged in, right? We plugged in the vector x, which was first coordinate pi over 2, second coordinate 0. And then in part B, we plugged the vector y into f, which is a two-dimensional vector, first coordinate 0 and second coordinate pi over 2. And then in part C, what we really did is, well, what is this vector? If x and y are defined like they are here in this observation, then this is actually the sum of x and y, right? This is actually f of x plus y. Let me just add an annotation here. Just this is relative to the observation down below. This becomes f of x, this becomes f of y, and this becomes f of x plus y. So notice that this is the case, right? F of x plus y, that's the left-hand side. That means you take the two vectors x and y and you add them up first, and then whatever the result is, plug it into f. On the right-hand side, each of those two vectors x and y are plugged into f separately, right off the bat. And then whatever the function returns in either of those cases, those two return values are added together. So those are conceptually different. And in this case, with this function, they are practically different as well. So actually, I'll keep writing in yellow just to keep this distinct from the original example. If we went f of x plus y, we got 1, 0. But f of x plus f of y, well, this is f of x because this is x, right? So this is our f of x, and this was y, so this is f of y. So this actually is 1, 1 plus 0, 0, which is equal to 1, 1. So, and I'm going to switch colors again. These are different. And that's important to notice. Okay? F of x plus y and f of x plus f of y were different values. So because of that, this function actually fails to be a linear transformation. Or let's just keep it simple here. We'll just say it fails to be linear. So at the beginning when I said, roughly speaking, what linear transformations are is that they're functions that have nice properties. This is an example of a function that doesn't have the nice property that we're, and I'll say more specifically what that property is on the next page.